All right, so why was Manal able to so easily get it at least close to the ground?
Force.
Pardon?
The force I was exerting on it.
Okay, but weren't they exerting a force also?
Yes.
So why were you able to overcome their brutal force?
Probably more than them.
So you're making the claim that with 2 fingers you exerted more force than they did as they were gripping it around. You had it wrapped around your hands, right?
Mm-hmm.
Those are strong fingers. There's another explanation. Unless you want to go into more detail, you could work to the correct answer from where you are at the moment. Anyone else?
Because of how long the rope was?
That has something to do with it. So what impact does the length of the rope have?
It would reduce how effective our force was.
Toward the middle, it would be the least amount of exertion.
So
Right?
you're saying that the force sort of gets lesser and less as you get to the middle?
As the rope is long, the longer the rope, towards the middle, there's less tension in it.
Now, actually, you'll find that the tension that they were exerting was pretty constant throughout.
Oh.
But there is something to do with the length of the rope, but not that. Anyone else? Okay. Carrie, which way were you pulling? In terms of the hallway, point.
Oh, that way. To the left.
All right. And Rachel, which way were you pulling? Which way were you pushing?
Downwards.
Anyone want to speculate about why she was able to get it so close to the ground, despite the fact that they were pulling?
Because the downward force was greater than the pulling on the left and the right.
You've seen the ballpark. Right. What was their effort mostly doing? Right, read my mind. Stay away from the dark places.
We were pulling, yeah.
Okay. You were pulling against,
An opposite force.
you were pulling against her.
Right.
So initially, how much were you pulling against her?
Nothing.
Right. That's critical.
Well,
Because almost all of their effort was spent fighting each other. Now as you pushed it down, what did you find about how hard it was? Did harder or easier or same?
Compared to the first time.
Yeah, well, as soon as you started pushing it down, did you notice anything as you got farther?
Yeah, it did get a little tighter.
Okay.
As I pushed down.
So initially, the forces that were being exerted were like this, and then Manal was pushing down like that. None of what, eventually I'll get a lot smoother on the names, Carrie and Rachel were doing was fighting her. At some point, they were pulling down like this, or you were pulling up because she was pushing down in the middle of the rope. And so now there's part of their force that is upwards. Part of it's still to the right. Most of the force that they're exerting is still fighting each other. But there is a little bit that's pulling up. And that's what's slowing her down. So what does this mean? Well, give someone a chance to show off before I actually write it down. What is the takeaway that I want you to have from this?
Every action has a reaction.
Uh,
I mean.
although true, it's a lot harder to pull from this. You will get into that detail later. The reason why I don't want to connect that right now is that is Newton's third law, we will get to it. That is probably the most abused and misunderstood of all the laws, so I really want to wait before we tackle that one.
Don't fight.
Pardon?
Don't fight.
Oh, well, okay, that's a good one. I was thinking something more physics related, but sorry, spoilers. Direction matters. If you're dealing with a quantity where direction matters, we are now dealing with something called vectors. And the math's just a little bit different than the math you've done before. Anyone know what, if direction doesn't matter, anyone know what it's called? What the other vocabulary word is? It's the math you've been doing since kindergarten. Not enough kindergarten teachers use this term. Scalars. Vectors and scalars. Vector. I'm going to put in the unhelpful word just a second. A mathematical construct. Yeah, I really don't like the term construct, but it really is the right word. In which direction and magnitude matter. A scalar starts out the same way. It's a mathematical construct in which only magnitude matters. So, a mathematical construct in which only magnitude matters. So that 2 plus 3 equal to 5, that's scalar math. That's the stuff, all I've done is I've taken presumably a new word and attached it to something that you've been doing for years. Vectors, on the other hand, anyone actually dealt with vectors before? Okay. Not usual in Physics 110 for anyone to have dealt with them before. All right, so, questions up to here before I keep going? All right, so how do you know if you're dealing with a vector or a scalar? Now, there are certain terms, certain words that are automatically vectors. Force is a vector quantity. Displacement is a vector quantity. Distance is a scalar quantity. So there are certain vocabulary words that we will do that we're going to do that will cover, that will automatically fall into one category or the other. But in terms of notation, there needs to be some symbol to represent the fact that we're dealing with a vector. And so if I have some quantity A, pick a letter if you don't like the letter A, just some letter. And I want to communicate to you that we are dealing with a vector, so direction matters. I put a little arrow over top of it. The arrow is always pointing in that direction, regardless of what the direction of the vector is. but that's just the symbol that's used. Another symbol that is used, generally when I'm writing on the board, I'll do what I call the half arrow, just because it's easier to write. On a test or quiz, because I'm using a word processing program, they do the full arrow like that, but this is what I tend to do in class. There's also the double print. I don't use this. There's actually only one time I actually use this, and for whatever reason, it's just sort of stuck. That's what I call the double print. And then some textbooks will use boldface. Your textbook doesn't. But if you're looking at other sources, some textbooks will just do bold, and I hope you can imagine why I don't do that in class. All right, so those are just the symbols that are used to represent the fact that we're dealing with a vector. And so if I have something pointing to the right, let's say this represents a force of, we'll just say 4 newtons to the right. And I want to be able to write that. I want to say I have 4 newtons going to the right. Here's one way of doing it. 4 newtons. So I write my force with the vector symbol over it is equal to 4 newtons to the right. However, as physicists, we don't want to write unless we have to. We want to write as efficiently as possible, so we want a shortcut so we don't have to write out the words to the right or left or up or down or any of that stuff. We don't want to write those words. So we have a shortcut. That really is a shortcut once you're used to it, and until you get used to it, you could just continue to write it out like that. The shortcut is, what I'm going to do is I am just going to put an arrow to the right, and I'm going to put this I with a hat on it. And every semester I say to myself, one of these days I'm going to remember what the actual name of that hat is. If you're using OpenOffice formula writer or equation editor, hat is the key word, but it's a grammatical mark in French, and I can never remember what that one is. Anyone had enough French to know what the mark's called? Okay. So now what I've done is I have defined that to the right is the equivalent of this I hat. I'll talk about what the hat means in just a second. So I can now write this as 4 newtons I hat. It's just shorter notation than having to write out the words. To the left, I could have also, well, let's do that then. So I have this 4 newtons going to the right. I could have, instead of saying I hat is to the right, I could have just said to the left is I hat. And so now my force would be negative 4 newtons I hat. The negative just means opposite. I hat is not always to the right. I hat is in whatever direction is convenient for you. Now, a lot of the things we'll do, horizontal, vertical, are really convenient, but when we get to something going down a ramp, that's no longer convenient, and we'll want to sort of change our coordinate system. We're going to basically make I hat down the ramp or something like that. All right, any other questions at this point? All right, so this hat, it is a symbol for a vector, but it's actually a symbol for a very special vector. If you ever see any letter with the hat over top of it, and I is generally the first one I do, this is known as a unit vector. The magnitude, because it's a vector, so it has a magnitude and a direction. The magnitude is right there in the name. The magnitude is equal to 1. No units, it's 1. For most of the unit vectors that we will use, the direction is what we say so. The direction for most is what we say. Or what I say, or what you say, that we don't have to have a general group consensus on it. Whoever's working the problem defines it. Just like right here, I just said I hat was to the right. Here I said it was to the left. I could have said it was up, but that wouldn't really help us since this one's to the right. Now the reason I put in for most is there is an exception. There is a unit vector that is automatically set, and that is r hat. That's an R. This is known as a radial unit vector. And it is away from the center. So if you have something that generally is going outwards, like if I have a light bulb and I turn it on, the light goes outwards in sort of a radial direction. That's the kind of situation where we use r hat. Gravitational pull will use r hat. The electric force will use r hat. And centripetal motion will bring in r hat. But that, for the most part, everything else will be using I, J, K. I think in 110 we don't go past J, I and J. Right. So what I've done so far really is just introduce notation and vocabulary. We haven't really gotten to any physics yet, other than the word force. Questions before I erase this? Although it is immortalized on film, or whatever the equivalent is. Oh, I didn't check the battery life was left. Oh well. All right, so let's add stuff. Woo! Adding vectors, yes! So let's just say I hat is to the right. And so I have a 4 Newton force that is to the right. And I'll throw a box into it. And I have a 3 Newton force that is acting to the right. Now notice that I made the 4 Newton arrow larger than the 3 Newton arrow. Properly, when you're drawing this, if I were doing this incredibly retentively, then I would have some scale. This would be 3 whatever units I'm using, and this would be 4 of them. So this would be 33% longer than that. And I want to know the total force acting on that box. Well, there are a couple of ways we can do this. One, we can use this. So the total force, I take 4 newtons I hat, because that's to the right, plus 3 newtons I hat, because that's also to the right. And without using a calculator, what does that equal to? Give me the whole thing.
7 Newton I hat.
That seems a whole lot like that kindergarten math you did. Don't worry, we'll change that in a second. The total force acting on that box is 7 newtons. Questions here before I make it more complicated? All right, let's make it more complicated. I got my box right there. I got 4 newtons acting to the right. I have 3 newtons acting to the left. The total force. Well, that's a new problem, so the question is, can I assume that I hat is to the right still, or do I have to redefine it? I should probably redefine it. On a test or quiz, if you do this at the very top of the test, then I'm assuming it covers everything unless you say otherwise. If you do it for an individual problem, then yeah, you would need to redefine it for the next problem. So let's go ahead and redefine it. Let's just say to the right is I hat. All right, so I'm adding the 2 forces because I want a total. So that is 4 newtons I hat plus
minus
yes,
3 I have.
yeah, there we go. And I know that was your intent. Just a lot of times on tests, people just drop direction because everybody knows what they're talking about. No, make sure units and direction are important. I'll show you a shortcut in just a moment, but don't forget direction. All right, so now we have 4 newtons I hat plus negative 3 newtons I hat.
And I have
All right. 1 newton I hat, that's the total force. Now, why this is important will come up in chapter 4 of the textbook. But once you know the total force acting on an object, you can then predict, you can then find out what the acceleration is. Once you know the acceleration, you can start predicting what the motion is going to be. That's ultimately where we're heading. But we're still in just chapter 2. Chapter 1, read for pleasure. Now, both of these problems are one-dimensional. All I needed was just an I hat, and I don't need any other letters, just I hat, and I've got everything covered. So, if it is a one-dimensional problem, and a fading marker, direction, again, so again, if. Direction can be defined by a plus or minus. Well, you're going to do a lot of one-dimensional problems in here, but we'll do some two-dimensional problems also. So once you get to 2 dimensions, you can't get away with just a plus. You need an I hat, J hat, something like that. So what I'm talking about here is, since this is a one-dimensional problem, I could have instead just said, hey, to the right is positive. And so then I just have 4 newtons plus 3 newtons is 7 newtons. My answer is positive, and I said positive was to the right. Or, same problem, let's say I said to the left was positive. Then that would be negative 4 newtons plus negative 3 newtons is equal to negative 7 newtons. Negative just means the opposite direction, and so since positive is to the left, negative would be to the right. So it's the same answer. But they look different because we are defining things differently. You know, in math class, x, y. Anybody do any axes other than x to the right and y up? Yeah, we're now saying, hey, we can do it this way. Or that way. Take that, math people. Over here, it's still a one-dimensional problem, it's still just left or right. Or I could rotate it and make it up or down. Let's say over here, I could make to the right, or left, as people say today. To the left positive, and so I had -4 newtons plus +3 newtons, or -1 newton. And negative just means opposite the positive. Now I know you're gonna be really upset this next bit. I was about to do two-dimensional, but we're out of time. So it's sort of like a cliffhanger. How do we deal with two-dimensional problems? And you'll just have to come back on Wednesday and find out. I'm glad all of you made it. I hope it's a good and hopefully not as stressful time as I'm picturing in my head. But we will make the best of it as we can. Was I difficult to understand because of the mask? I might have been difficult to understand because of the topic, but that's separate. Oh, the lab. On Friday, I think that's the lab that all of you have. It's Friday. At some point today, I will, on Blackboard, if you go under labs, there'll be a lab that shows up. I think it's cleverly called graphing, maybe graphing lab. I want you to have that printed out before you come into class on Friday, or before you come to lab on Friday, have that printed out. If you have printer issues or something like that, I can deal with that. If it's a one-off or if it's ongoing, just, we'll deal with it as it comes, but the ideal is that you print out that lab before you walk in on Friday. I don't think it's posted at the moment.